What if I told you that by the end of this lesson, you'll have used a quantum computer to solve an actual physics problem, using the same fundamental calculation that physicists use to study real magnetic materials? Well, that's exactly what we're about to do. If you've watched Lesson 1 and 2, you've by now run your first quantum circuit and learned the basics of quantum computing, how quantum states are represented and how gates act on those states. But now it's time to put all of this into practice and solve your first real problem on a quantum computer. In this lesson, we'll follow these principles to simulate the interaction between two spins, which you can think of as tiny magnets. But don't think too hard about the accuracy of that metaphor for now. For this problem, we're going to use two qubits, one for each spin in our model. Each spin can be pointing either up, qubit state 0, or down. We'll call that qubit state 1. We're going to say our spins have an antiferromagnetic interaction, meaning that they want to anti-align, so that when one is up, the other one wants to point down, and vice versa. Now, suppose that there is also a transverse magnetic field that exists, pointing from left to right in our system. This field can flip spins, which causes the system to form superpositions instead of staying in a single up or down configuration. Now, this is a simple toy problem, but it has obvious extensions to real research problems that scientists are currently trying to solve. And we can describe all of these effects using a mathematical object called a Hamiltonian. A Hamiltonian is basically the total sum of all energy contributions in a given model. For our arrangement of spins, we would have this Hamiltonian, where J is a coefficient controlling the strength of the interaction between spins, and H sub x is a coefficient for the strength of the external magnetic field. Z0 and Z1 rewards or penalizes the spins depending on whether they are aligned or anti-aligned, and X0 and X1 represent the spin flipping effect of the magnetic field. We will use this mathematical description to answer the question: if we put our spins in a particular state, what is the energy of that state? Again, this is a very simple system, so it's fairly easy to answer that question. But as you will see, this is the exact same type of question that we can expect quantum computers to be able to solve even when the system is much larger and more complex. We are going to now run two different sets of experiments. One will tell us which states our spins are actually in, and then the other will tell us the energy of the configuration. Luckily, Qiskit has two different tools called primitives that are set up to do exactly that. We're first going to use the sampler primitive to tell us the spin states. Let's begin to code. So first, I'm just importing the exact same things as I did last time, our Qiskit Air simulator in case you want to use the simulator, and all of our quantum circuit and visualization tools. Okay, that all looks good. When writing Qiskit code for an experiment, it's useful to follow the Qiskit patterns framework. This framework breaks a quantum computing task into 4 steps. Number 1, map the problem to a model that can be represented by quantum circuits. 2, optimize the circuit to run on a specific backend. 3, execute the optimized circuit on the selected backend. And 4, post-process the raw measurement data. Now we'll begin mapping. For this mapping step, we just have to decide on the state we'd like to prepare. Then we write a circuit that prepares and measures this state. Let's prepare an entangled Bell state similar to the one we made in the first lesson of this course, which is a state of 1 over root 2, 1, 0, minus 0, 1. For the sake of brevity, I have just pulled open the old notebook we used and copied and pasted the circuit. But this time, I added 2 rotation gates after our C0 gate to make sure that we get the exact Bell state that I just described. If you have any questions about this circuit, please go back and check out lessons 1 and 2. So since we already have our quantum circuit, the mapping step has been taken care of. Next, we need to optimize. Before we run our circuit on a quantum computer, or a simulator if you prefer, or you used up all your runtime, we need to prepare it for execution. This is the optimization step. During optimization, we choose the backend, either a real quantum computer or the simulator. Then we assign our circuit's qubits to physical qubits on the device. Next, we rewrite the circuit using only the gates that the specific quantum computer that we selected can actually perform. And finally, optionally implementing error mitigation and suppression techniques to reduce the effects of noise. Now, in Qiskit, almost all of this can be handled automatically by the transpiler. Once you pick your backend, the transpiler does almost all the work to make your circuit ready for execution for you, so you don't have to manually adjust the gates or the qubit assignments. The transpiler also offers different optimization levels, which can help reduce errors if needed. To learn more about errors and error mitigation, see the Quantum Computing in Practice course playlist. But for now, I'm going to implement our runtime service and load my account just as I did last time. And I'm going to also implement from the transpiler a preset pass manager that will already handle everything that I just described. My code is thinking. Okay. All right. Implementing the pass manager. And then I'm going to draw my circuit. So you can see here, now the circuit has been redrawn using gates that are native to the quantum computer that I selected, which is IBM Torino in this case. By using this preset pass manager to handle everything hard, we are actually already ready to execute our circuit. I'm going to import the sampler primitive. If you're interested in using a simulator for any reason, you can run this chunk of code instead. Now we'll run our circuit using the sampler with 100 counts or 100 shots, and then collect the results like so. All right, that finished. Lastly, post-processing. We have all of our counts now, so this step will just include plotting our measurements in a histogram since we are not going to implement any error mitigation for now. There we go. Here's how we plot our counts. And you can see that the majority of counts are either 0, 1 or 1, 0, meaning that one qubit was measured to be 0, then the other was measured to be 1, and vice versa. This is consistent with the Bell state that we prepared. There's also a very small amount of the 0, 0 state that was measured, but this is due to errors. And if we were being really picky, we could implement some techniques to minimize this even further. But since only one error occurred for the whole experiment, I'm pretty satisfied with these results. So let's move on. Now for our next experiment. We need to measure the energy configuration of what we set up. To do this, we are going to use the other Qiskit primitive called the estimator. Now, recall our Hamiltonian. Each term in the Hamiltonian tells us how a certain combination of spins contributes to the energy. In Qiskit, we can represent these terms as Pauli operators, which are just labels for simple actions on qubits. Now, the Z0, Z1 acts with a Z on both qubits. The X0 acts with an X on the first qubit, and an X1 acts with an X on the second qubit. In Qiskit, we will use a function called sparse Pauli op, which will translate these Pauli terms into observables the quantum computer can measure. The syntax for this is as follows. You can see it right here, where ZZ shows that we are acting on both qubits, 0 and 1, with Z, and IX and XI represent acting on qubit 0 and then qubit 1 with X, while respectively leaving the other alone. And just as before, we create our circuit using the same gates. Note that here we omitted the qc.measureAll line in our code. This is because with the estimator, we don't need to specify where to measure in the circuit. We will just tell it which observables we want estimated, and Qiskit takes care of the measurements behind the scenes. Now, the optimization step for this experiment is the same, as long as we also remember to write our observables in terms of the gates that the quantum computer can understand. I'm just going to reload my runtime service. And that's still the same back end. All right, so that's still the least busy one. And now we're going to redraw our circuit. All right. To execute this experiment, we will load the estimator and as arguments, give it both the circuit and the observables that we want to measure. So, import the estimator. And then we are importing backend estimator v2. Finally, for post-processing, all we need to do is print the 0th index result from the job. This is the energy that we calculated from the entire system. Now, one fun game you can play here is to try and find an even more accurate energy than I did. How will you know if it's more accurate? Well, there's actually a pretty cool trick you can play here, because any energy that's lower than the one that I calculated is actually going to be more accurate. How do I know this? Because all physical models tend to want to settle in what's called the ground state, which is the lowest possible energy configuration. It takes the least amount of work to remain in that position. Physicists call this the variational principle, but regardless of what you call it, it intuitively makes sense that the system wants to be in a low energy configuration. And you can measure an energy that is even lower than what you previously found, then that one is the one that's going to be closer to the true value. So go ahead and tweak the circuit and see if you can calculate a lower energy than what I did, and post your result in the comments below. We have just one more lesson in this course where we're going to talk about how to separate quantum fact from quantum hype and all of the different applications that we expect quantum computers to be able to access in the near future. So don't miss it.